Late summer, 1970. The California sun is brutal, the kind of heat that makes asphalt shimmer and turns a garage into a furnace by noon. A brand new Chevrolet Chevelle rolls into a local shop in Southern California. The paint still gleams. The interior still smells like the showroom floor. But something's wrong. The owner steps out, frustrated, exhausted. He's been here before. He says the engine overheats in traffic. It runs fine on the highway. But the moment he hits a red light or gets stuck behind a slow truck, the temperature gauge climbs. Fast. Oil pressure drops at idle. Coolant disappears without a trace. No puddles under the car, no visible leaks. Just gone. And every time the mechanic pulls the heads off, the head gasket looks like it's been chewed up and spat out. Burned edges, blown sections, discoloration around the cylinders that tells a story of heat way beyond normal operating temperatures. The badge on the fender says 400, but what almost nobody knew at the time is that this engine was already becoming one of the most frustrating small blocks ever built. You think you know Chevy's legendary small block story? Not like this. Because the 400 cubic inch small block wasn't just another V8, it was the biggest small block Chevy had ever attempted to mass produce. A torque monster on paper, a street king in theory. An answer to every buyer who wanted muscle car power without big block weight or big block fuel bills. But in the real world, it became the engine that made mechanics swear under their breath. The engine that ate head gaskets like snacks. The engine that confused dealership technicians, frustrated backyard builders, and sometimes made seasoned professionals refuse the job entirely. Because fixing a 400 wasn't like fixing a 3M50, and almost nobody understood why. By 1970, the muscle car wars were at full throttle. Ford had the 351 Cleveland, a high-revving masterpiece with canted valves and massive ports that could breathe like nothing else in its class. Chrysler had the 340 and the 383, machines built for straight-line speed and weekend drag strip glory. Insurance rates were climbing, emissions regulations were looming on the horizon, and buyers wanted torque, not high-revving race motors that needed to be wound up to 6,500 RPM to feel alive. They wanted something that could shove 3,600 pounds of steel off the line with authority. Something that felt strong at every stoplight. Something that didn't need to scream to deliver power. And General Motors was listening. So Chevy did something bold. They took their proven small block architecture, the same basic design that had powered winners since 1955, the same platform that gave birth to the 283, the 327, the 350. Engines that had earned their reputation in everything from family sedans to Le Mans prototypes. And they pushed it way past what it was ever meant to handle. The new 400 used a massive 4.125-inch bore and a 3.75-inch stroke. That gave it 400 cubic inches of displacement, bigger than the legendary 396 big block in some configurations. But it still fit in a small block chassis. It still bolted to small block transmissions. It still weighed hundreds of pounds less than a proper big block. On paper, it looked brilliant. A torque monster hiding in a lightweight package. In its early form, the 400 small block ran 10.25.1 compression and produced 265 horsepower and 400 lb-ft of torque. These were gross horsepower numbers, measured at the flywheel without accessories. But even by the standards of the day, that torque figure was impressive. Later versions dropped compression to around 8.5.1 as emissions tightened and unleaded fuel became the standard. Horsepower fell into the 150-180 range by the mid-70s, numbers that looked pathetic compared to what muscle cars had delivered just a few years earlier. But torque stayed strong. Even smogged-down versions still made around 320 lb-ft. And that torque? It came in low, around 2,400 RPM. Perfect for street driving. Perfect for heavy cars like the Chevelle, Impala, and Monte Carlo. Perfect for highway passing. Perfect for pulling boat trailers up hills without downshifting. Buyers loved what the 400 could do. But there was a problem. Actually, several. And they started showing up almost immediately. To get that 4.1 on 25-inch bore into a small block casting, Chevy engineers faced a fundamental engineering challenge. The small block architecture was never designed for bores that large. The original platform maxed out around 4.00 inches, maybe 4.03 with some creative casting. But 4.125, that required removing something important: the water passages between the cylinders. These are called siamesed cylinders. Instead of coolant flowing freely between each cylinder wall, the way it did on a 350 or a 327, the 400 cylinders were cast directly against each other, metal touching metal, no space for coolant to circulate where it was needed most, heat building up fast. Most people didn't realize what that meant at the time. It wasn't the kind of thing salesmen mentioned on the showroom floor. It wasn't in the owner's manual. It wasn't something even most dealership mechanics fully understood in those early years. Because now, cooling became a nightmare. At idle or in traffic, those Siamesed cylinders would trap heat right in the center of the block. Think about what happens when you're sitting at a red light in August. The radiator fan is spinning, coolant is circulating, but the engine isn't making power. There's no airflow through the radiator fins. Heat builds faster than the cooling system can remove it. In a normal small block, that heat would dissipate through the water jacket surrounding each cylinder. Coolant would carry it away to the radiator. But in the 400, temperatures between the cylinders could spike dramatically. 50 degrees hotter than the rest of the block in some cases. And when metal gets hot, it expands. Cylinder walls would distort. The perfectly round bores that pistons needed to seal against would become ovals. Slightly, imperceptibly, but enough. Head gaskets would lose seal. The clamping force holding the heads against the block couldn't compensate for uneven thermal expansion. Gaps formed, microscopic at first, then larger. Combustion pressure would leak into the cooling system. That's why coolant disappeared. It wasn't leaking onto the ground. It was being pushed out of the overflow, slowly, constantly. Every time the engine ran hot, a little more escaped. Mechanics started seeing the same thing over and over again. Bubbling radiators, mysterious coolant loss that couldn't be explained by external leaks. Overheating that made no sense, especially when everything else in the system checked out fine. Brand new radiator, brand new thermostat, brand new water pump, brand new hoses, still ran hot. One veteran shop owner from Riverside reportedly said, "You could put 3 radiators on it. Didn't matter. It still ran hot. I thought I was losing my mind until I figured out what was actually going on." But Chevy knew this would happen. Engineers in Detroit weren't stupid. They understood the physics. They knew that Siamesed cylinders would trap heat. They knew that coolant flow would be compromised in critical areas. So they added a workaround: steam holes. Tiny drilled passages in the block and heads that allowed trapped hot coolant and steam vapor to escape from between the Siamesed cylinders. These holes were small, maybe 1/8-inch diameter, but they served a critical function. Without them, steam pockets would form. Vapor lock would prevent coolant from circulating, and temperatures would spike in exactly the areas where you couldn't afford them to spike. The steam holes let that trapped vapor escape. They allowed fresh coolant to flow in. They kept the system circulating even in the worst hotspots. And here's where the real nightmare began. Because the 400 used specific cylinder heads, heads designed for that engine, heads with steam holes drilled in the correct locations to match the block. But if you replaced those cylinder heads with standard small block heads from a 350 or a 327, and didn't drill matching steam holes, the engine would overheat badly. Those standard heads would seal off the escape routes for trapped vapor. Steam pockets would form immediately. Coolant would stop flowing in the areas that needed it most. Temperatures would climb, metal would expand, gaskets would fail. Head gaskets would fail within weeks, sometimes days, sometimes on the drive home from the shop. Bearings would show signs of heat stress. The thin film of oil protecting them would break down. Metal would touch metal. Scoring would appear on the crank journals, oil would thin out at high temperatures, viscosity would drop, the pump would still spin, but the protection would vanish. Oil pressure would drop at idle, exactly when the engine was already running hottest, exactly when it needed lubrication most. Pistons would scuff the cylinder walls as expansion tightened clearances beyond safe limits. The careful engineering that allowed for thermal growth assumed normal operating temperatures, not the extremes the 400 was seeing. You can probably guess what happened next. Backyard mechanics started swapping heads from 350s onto their new 400s. They had good intentions. Maybe they wanted better flowing heads for more power. Maybe they found a cheap set at a swap meet. Maybe the original heads cracked and they grabbed the first replacement they could find, with no idea they needed those holes. And engines started dying everywhere, junkyards filled with 400 blocks that had no obvious damage. They just ran hot. They just ate gaskets. They just never seemed to work right no matter what you did. But overheating wasn't the only issue. The 400 small block also had something no other production small block Chevy used: external balancing. Most small blocks, like the 327 or 350, were internally balanced. Their crankshaft counterweights handled the entire rotating assembly without help from outside components. You could swap flywheels, flex plates, and harmonic balancers freely. As long as the parts fit, they would work. But the 400's longer 3.75-inch stroke meant heavier pistons and rods, more mass moving up and down at high speed, more inertia to counteract, more weight that needed balancing. The crank simply didn't have enough room inside the block to carry all the counterweight mass needed for smooth operation. So Chevy moved some of that balancing weight outside, into the harmonic balancer and the flex plate, or flywheel, depending on transmission. These parts had carefully calculated offset weights that completed the balance equation. Without them, the rotating assembly would be out of balance. The crankshaft would wobble, vibrations would travel through the entire engine. Now, if you installed the wrong flex plate, the one from your buddy's 350 that looked identical, or a neutral balanced balancer from a standard small block rebuild kit, the rotating assembly would vibrate violently at certain RPM ranges. Main bearings would wear out prematurely. The constant vibration would destroy the carefully maintained oil film that separated the bearing surface from the crankshaft journals. Crank journals would score. Metal particles would circulate through the oiling system. Contamination would spread. In extreme cases, the rear main seal would leak almost immediately due to crankshaft oscillation. The seal depended on consistent, smooth rotation. When the crank wobbled, the seal couldn't maintain contact. One racer from a 1972 dirt track series in Central California reportedly said, "It shook so bad at 5,000 RPM you thought the dash was coming off. Mirrors were useless, couldn't even see straight, took us 3 rebuilds before someone told us about the balance issue." And because externally balanced parts looked almost identical to standard ones. Same bolt pattern, same diameter, same overall appearance. Mistakes happened constantly, especially in the aftermarket world where parts were less carefully documented, especially in an era before internet forums and YouTube tutorials, especially when the only way to learn was through expensive, frustrating trial and error. What they discovered next changed everything, because even when properly balanced, with the correct externally weighted flex plate and the correct harmonic balancer, the 400 still had one more fatal weakness. Remember that 4.125-inch bore? The one that required siamesed cylinders and steam holes? It pushed the limits of the small block casting to the absolute edge. Cylinder walls were thin from the factory, not dangerously thin, not thin enough to fail under normal use, but thin enough that there was almost no margin for error. Overbore it just 0.030 inches to clean up a worn block, and you were already flirting with disaster. Go to 0.060, the way you might with a 350 during a high-performance rebuild, and cracks could form between the siamesed cylinders under load. The casting simply couldn't handle the reduced wall thickness combined with the thermal stress combined with the cylinder pressure of combustion, especially in high-performance builds running 9.5.1 or higher compression, especially with headers that increased exhaust gas temperatures, especially with aggressive ignition timing that maximized cylinder pressure. At sustained RPM above 6,000, cylinder pressure combined with thermal expansion would stress the casting beyond what it was designed for. Blocks would split. Hairline cracks would appear between adjacent cylinders, sometimes invisible to the naked eye, but enough to allow combustion gases to leak, enough to allow coolant to seep into places it didn't belong. Coolant would leak into the oil. You'd pull the dipstick and see milkshake. That distinctive tan color that meant water had emulsified with the oil. That meant bearings were already damaged. That meant the engine was already dying. Engines would hydrolock or seize completely. Mechanics eventually learned to be cautious. Machine shops started sonic testing 400 blocks before boring them, ultrasonic thickness measurements that could reveal exactly how much material remained in the cylinder walls. Many were too thin to safely machine at all. They looked fine externally. No cracks, no obvious damage, but the measurements told a different story. 0.062 over bore would leave wall thickness below safe minimums. Sometimes even 0.030 was too much. So builders began installing cylinder sleeves just to save usable cores. Press-fit steel or iron sleeves that replaced the worn cylinder walls entirely. They allowed the block to be rebuilt without depending on the original casting thickness. Expensive, time-consuming, but necessary. And even that wasn't always enough to save a core that had already been overbored by a previous owner who didn't know any better. By the late 1970s, the automotive landscape was changing rapidly. Insurance companies were already raising premiums on muscle cars equipped with large displacement V8s. Young drivers couldn't afford coverage, sales dropped, dealers couldn't move high-performance inventory. Emission standards tightened after the Clean Air Act of 1970. Catalytic converters became mandatory. Compression ratios fell to accommodate unleaded fuel. Horsepower numbers dropped across the entire industry. The muscle car era was ending. Production of the 400 small block ended in 1980. Tooling was retired. Blocks were scrapped. The engine that had caused so much frustration was quietly discontinued without ceremony. But here's the twist, because despite all its flaws, despite the overheating and the gasket failures and the balancing issues and the thin cylinder walls, racers loved it. That long 3.75-inch stroke made incredible low-end torque. More stroke meant more leverage on the crankshaft. More mechanical advantage converting combustion pressure into rotational force. In circle track racing, where pulling hard out of corners mattered more than top-end RPM, a properly built 400 could dominate. You didn't need to wind it to 7,000 RPM. You didn't need screaming valve springs and aggressive camshaft profiles. You just needed grunt, low in the power band, available exactly when you needed it. With aftermarket heads that had properly located steam holes, the cooling problems disappeared. With correctly drilled steam holes in replacement castings, vapor lock became a non-issue. With forged pistons designed for the application, thermal expansion was controlled. With balanced rotating assemblies using the correct external weights, vibration vanished. Race-prepped 400s were producing well over 450 horsepower by the 1980s. Some were pushing 500. Quarter-mile times dropped into the mid-11s. Terminal speeds exceeded 115 mph, numbers that would have been impressive for big blocks just a decade earlier. And the torque, still there, still massive, still available right off idle. So how do you turn a mechanic's nightmare into a race winner? You fix what Chevy couldn't. Better cooling through improved water pump designs and higher flow thermostats. Thicker aftermarket blocks cast specifically for racing applications. Improved oiling with high-volume pumps and windage trays. And precision balancing done on modern equipment with modern techniques. Today, original 400 small blocks still show up in vintage builds and dirt track cars. Collectors seek them out. Racers hoard good cores. Machine shops know exactly what to look for. But now, builders know the secrets. Drill the steam holes in any replacement heads. Match them exactly to the block passages. Don't assume anything. Use the correct externally balanced flexplate or flywheel. Check the part numbers. Verify the weights. Never overbore without sonic testing. Know exactly what you're working with before you cut. And respect the limits of the casting, because the Chevy 400 didn't fail because it lacked power. It failed because it pushed the small block platform beyond what 1960s engineering could reliably support. It ran hot, it vibrated, it cracked, but it also made torque like nothing else in its class. And that's why mechanics hated it. But racers never let it die. If you enjoyed this deep dive into one of Chevy's most misunderstood engines, let me know what you want to see next. Another forgotten V8, another rivalry, another piece of automotive history that didn't go the way anyone expected. And make sure to subscribe, because the next story might be even wilder.